Good morning, everyone. I'm Zhen Yang from Nanjing University, People's Republic of China. Today, I'm very glad to say that it's really a great honor for all of us to present our work here and share our new ideas with everyone here. Our work was green water treatment technique based on natural polymeric materials, and the highlights of our works are 3 points. The first one is in our work, novel water treatment agents were prepared from our mother nature. And the second point is that our green materials enjoy high water treatment efficiencies in both laboratory and pilot scales. At last, we did cost test and show that our materials are cost effective. So let's begin. It's the content of our work. And the first part is our creation motive. As we all know, our world suffers the disadvantages of water pollution. According to the 2 most influential scientific journal reports, the water pollution is getting serious nowadays. And here is the graph. As we can see, many regions in the world suffer from these disadvantages. Of course, the mainland of China and Taiwan are included. Take the mainland of China as an example. Most of the clean rivers where we can swim when we are young now become very turbid and even smelly. That's very sad, right? So we need some technology to solve this problem. In recent decades, various techniques have been developed. Among them, most of them are very attractive for fundamental study, but for real application, some of them are too expensive. So we focus on these 2 kinds of technologies. They are very widely used and low cost, easy operation. When using these 2 techniques, chemicals are needed. For flocculation, it's flocculants, and for adsorption, it's adsorbents. And these are traditional materials for these 2 processes. They are very effective and have been confirmed for several years. However, they suffer 2 many disadvantages. The first one is secondary pollution, and the second one is high price. Especially the first shortcoming is intolerable. Why? Because changing one pollutant to another is meaningless to us, to the world. So we focus on replacement for these traditional materials. We focus on natural polymeric materials. What's natural polymer? They can be chitin, they can be organic acid, they can be cellulose, and they can be starch. And I'm sorry, some of them made you feel hungry, right? But our decision doesn't make which one is more delicious. We pay attention to which one is cost effective. So we focus on these 2 kinds of natural polymer materials. They enjoy 4 advantages, including large amount and low price and 2 bio features. So we are prone to say we are porters of nature, and natural polymer are even called 21st century's green water treatment agents. These 2 points just hit the topic of our competition, green tech. So here, let's come to our work. At the very beginning, we prepare materials. In real water, usually the contaminants are surface charged. They can be negatively charged or positively charged. So 2 flocculants and 2 adsorbents are prepared on the basis of their charges. After that, we did water treatment tests in both laboratory scale and pilot scale. As last, we did cost accounting to prove that our materials has greater potential, great application potential. So it's the material preparation part. After preparing the material, both the spectral analysis and zeta potential measurements prove that our materials have been successfully prepared. Then we did water treatment test in laboratory scale. It's a flocculation test, and it's the equipment we use, flocculator. We use 3 kinds of model wastewater, including colic suspension, humic acid solution, and hematic suspension. They are normally widely available in real water. And 3 kinds of other flocculants, other traditional commercial flocculants are used as comparison. These 3 figures show that our materials enjoy 2 advantages: the low optimal dosage requirement and the very high water treatment efficiency, especially the low dosage requirement. You can see that most of them are 1 log unit than traditional ones. Later, we did adsorption test. It's equipment. and absorption column. And we use two kinds of normally available dyes as model water, the Ag25 and the MB solution. And of course, our materials further enjoy this high absorption capacity in comparison with traditional ones. And later we did the recycle test. After several circles, we can see that our materials, our solvents, can still be used without capacity loss. And furthermore, we should always note that our materials are from our mother nature and are biodegradable, so disposal is not a problem in comparison with traditional ones. Later, we did this test in pilot scale. In fact, it's more important for us because it gives us direct guidance for whether this material have real industrial application, because fundamental study is too far away from the real application. Both the preparation part and water treatment are carried out in much larger apparatus, and it's the figure of our apparatus. The apparatus was designed ourselves. Of course, this afternoon you will see a mini model of this apparatus, which is made ourselves in the lab. We use one kind of flocculants and one kind of absorbents as a combination. And here is a traditional combination of inorganic flocculants and activated carbon. And it's the Chinese standard for drinking water, GB5749. So from the figure, we can see firstly, the water treated by our materials fully satisfies the requirements for Chinese standard. More importantly, we can see that compared with traditional ones, all of the key parameters of water treated by our materials are much better than the traditional ones. So if we see that the water treatment tests in laboratory scale make us happy, here the results make us excited. But there's always a but. We should know that when we want to put it into real application, what's the cost? So we did cost accounting, and here are the unit cost of our materials compared with traditional ones. We can see that for absorbents, our materials are at least comparable to traditional ones. And for flocculants, they are lower than synthetic polymer ones, but seem to be higher than inorganic ones. But we should know that, as aforementioned, I have told you that our materials' optimal dosage is usually 1 log unit than the traditional ones. So let's make it easier. Take the water from Yangtze River as an example. For treating 1 ton of water, this is the cost of our materials. And these are the traditional ones. We can see that it's much lower. So this result further confirms the application potential. So let's make a conclusion. The first is that, as I have said, our material was successfully prepared from our mother nature. They are green, they are biodegradable. And then we did tests in both laboratory and pilot scale. They show high water treatment efficiencies. At last, they are very cost effective. And at last, we can see that in this work, green water treatment based on natural polymeric materials is built and enjoys greater application potential. In fact, several Chinese innovation patents have been applied, and more than 10 scientific papers have been published, in which one of us is the first author. And at last, I'd like to thank to Techno Group for providing us this valuable opportunity to present our work here. And thanks to every expert here today. And thanks to Nanjing University, especially to Students Affairs Office. Thanks to Professor Zhu Chengjian and Dr. Xinhua Li and Wu Ke. And thanks to our advisors, Professor Dr. Yang Hu, and my partners, Yan Han, Li Haijiang, Wu Hu, and Cai Tao. Here are a picture of us. Thank you all. Thanks for your attention. Okay.
Okay, thank you very much for your presentation. I think I have 2 questions, okay? Try to clarify something, okay? So your technology, your product is trying to replace the conventional polymer and absorbent, right?
Yes.
Okay. So could you compare with the other polymer, like the polyamide? also the polychlorine aluminum chloride, and so. And for the anti-carbon, have you considered with other so-called granule anti-carbon and also the powder anti-carbon? Okay, this is the first question. And the secondly, you try to introduce your technology or your product, you have to care about the source water quality or the chemical characteristic of the source water. For example, if you treat the higher turbidity, okay, NTU is very high. Okay. Also, if the organic iron, organic acid is very high. So, do you have any data indicate how successful if you're facing those very poor contaminated source water? There's two questions.
Yes, these questions are very good. Well, as for the comparisons, we have made the comparisons between the polyamides and the polyalums have already been made in this presentation. Well, let's see these figures. The left is our flocculant, and the left is the polyaluminum chloride. I'm sorry that there isn't a detailed note. And the right is the polyamide, and we can see that our efficiency is at least comparable with these commercial flocculants, and our dose is much lower, and thus the cost can be reduced. And the second question, well, in our laboratory, we can only try the synthetic water samples, but in the pilot test, we've tried the water from the Yangtze River, and the NTU here is about 30 to 40, and the turbidity is about 30 to 40 NTUs, and the iron is about in the medium level, and the water samples with containing high turbidity and iron content, we will be tested later because the test is time costing.
Pair with the amberite, right? There's a synthetic organic from the Roman hearts, right?
Yes.
It's amberite.
Yes.
Okay.
In the chart where you have 5 cycles of recovery, what are you recovering? The recovery of the flocculant and the absorbent, or the recovery of hematite and kaolin?
The flocculant has used the flocculant because the dose is very, very small, about 1 ppm per about at ppm level. So usually in the water treatment techniques, the flocculants are usually not recycled. It is the adsorbents that are recycled. And the adsorbents are recycled using brines, using concentrated salt solutions, and they can exchange the ion.
Since it is a carbon source, right? You use starch, so would it increase the biological oxygen demand afterwards?
Well, the starch is itself in the ecosystem, in the cycle of the ecosystem. It's a link. So as the ecosystem itself, if we put the starch here, it will also degrade.
Sorry, time is up.
Thank you.
谢谢。
I'm very glad to introduce our work to you. Our work is the green water treatment technique based on natural polymer materials. We are from Nanjing University.
Okay. Nanjing University. Okay.
Yes. The key material and please. The key material in our work is the green water treatment materials. They are prepared from natural polymers. This material is prepared from cellulose.
Cellulose and
And this
starch.
is from starch. And they are effective, and they are effective both in efficiency and cost. Then let me show you how they deal with the contaminated water. This is our demo device. This is the raw water. As you see, it's turbid and muddy. Then our treatment begins. The water was first pumped into here, the flocculation section. Here, the starch-based flocculant is added. This flocculant is green and biodegradable, and it's also very effective. The dose of it is only 1/10 of ordinary ones. Here, the flocculant combines the small particles that are suspended in the raw water, mainly choline and humic acid and so on. The small particles then form larger particles called flocks. The flocks, they are much larger and heavier, and so they are much easier to be removed. After the flocculation, there will be a place for the flocculants to settle, for the flocks to settle, and then it is the inclined place settling tank. The water samples flow through several block plates and into this tank. Here, there are many inclined plates. They serve to slow down the flow and offer surfaces for the flocks to settle. As we can see, there are already many flocks that have settled on the bottom and on the plates. And from
Did you measure the alkalinity, also the zeta potential, in order to find the optimal dose? Introduce it here.
Yes,
you
yes.
do have.
Yes. And then from the head to end, the water has been clear. But still, there may be some invisible small molecules that are hard to be flocculated to remove. So we put this absorption column in case to remove these invisible pollutants. The adsorbents here are prepared from cellulose. The cellulose are from waste papers, and the waste papers can thus be recycled. Then the flow through the pump and then come through this absorption column. The green.
The absorption and the small particles supporting the filtration process. So the colloid is not good for the absorption process. You have to know that. Otherwise, you will increase your pressure drop. Okay, the absorbent is good for treat the small trace organics. It's not good for the absorption process. You have to know. Two that's different functions.
There is also filtration function.
Yes.
The upper and bottom are filtration, and the middle is absorption. Then in absorption column, the soluble and dissolved contaminants are removed by our green absorbent. And finally, it was pumped and flow out of the flow in the effluent tank. As you can see, the water has been much clearer, but still, it can only be drank after disinfection using chloride. And this, as you can see, is untreated water. It's still turbid and muddy.
This is artificial, right? You use chlorine and hematite.
Yes.
What are in there? What kind of contaminants?
There are and humic acid. It's a common content in raw waters like Yangtze River, Kwai River, and in many lakes. So this is our green water treatment process.
So you use all natural materials. Yeah. Are you the first one to use these two kind of materials? I think it should be others.
先到。有个环境学院，还是环境学都有。